Um, yeah, thanks for having me, everyone, and for inviting me, Zishan. What they probably didn't tell you is yesterday we had the Macquarie session, and everyone at Macquarie was working on different things. This is the RMIT session, and all three talks are very closely related to one another. And I didn't see Nick's talk before this, so there's a bit of overlap, but that's fine. So I'm going to be telling you about bosonic codes and continuous variable quantum information. But first, here, this is my career trajectory. I just wanted to point out I did my PhD with Ivan, who's in the audience, and so did Gavin. Gavin was Ivan's first PhD student. Second. And then I did a postdoc with Gavin, and that's where I met John at one of these sessions where he would show up for 2 weeks with a bottle of whiskey and make a bunch of noise and no one could work. And I told Zishin, I was actually at that satellite brainstorming meeting, but I didn't get invited to Shanghai. But nothing came of it anyway, so it's fine. And then I worked with Nick for 4 years at RMIT as a postdoc, and then went to Kyoto University as a glorified postdoc, basically. And anyway, so here I am back again as a postdoc this is my like 8th or 9th year of postdocing. But you know, that's what I'm into. I don't have to beg for money unless I want to. I don't have to teach. It's great. I spent a little bit of time in Xanadu. So yesterday, I decided I would take a look. So I met John at Macquarie, and we exchanged Facebook, and that's how we talk to one another using Messenger. But my name on Facebook is not my real name. I have an internet pseudonym that I wasn't trying to be super tricky or anything, but when I set it up in 2007, I just figured at some point I might have an employer that would Google me, and you know, it would be a little bit harder for them. But anyway, my Facebook name is Quinn, which is that's my middle name. And John forgot that my first name was Ben. We met in person, and he called me Quinn for the rest of his life. And I never corrected him. But I went back and looked at the last message he sent me, because I asked him for some advice on writing a DECRA. And you can see when he sent this message and how appropriate it is, you know, with respect to this code of misconduct that you heard yesterday, which is basically you can lie as much as you want to get the money. All right, so I'm going to tell you about continuous variable quantum information. So what we're interested in this setting is some degree of freedom of some quantum system that has a continuous spectrum. And I'm going to be talking exclusively about, you know, quantum harmonic oscillators. So in this case, if it's an actual, like a mass or something in a harmonic potential, you can think of position and momentum as being position and momentum. But I'm an optics guy, so these are just labels. They really represent properties of the electromagnetic field. They're just the two-phase quadratures of the electromagnetic field, which can take on various values. And we can represent pure states with wave functions. So just put a few of the interesting wave functions up here, right? We have a trivial Gaussian state, vacuum, a super fancy cat state, and then an extremely fancy, you know, multi-squeezed cat state, the GKP state that Nick was talking about. So the main topic of my talk here is bosonic error correcting codes, which is the idea of encoding qubits into systems that have some continuous degree of freedom, but not always. What's more important, I think, is that the physical system has a really large Hilbert space. And in fact, quantum harmonic oscillator has an infinite dimensional Hilbert space, you know, countably infinite in the energy eigenstate basis, or continuous with respect to, you know, the electric field amplitudes. Why qubits? Well, they form the basis for all these, you know, quantum information protocols. I know that some of these, particularly communication metrology and simulation, don't require discretization, but quantum computing does because of error correction. To deal with errors, we need to use error correcting code defined over qubits. So this is a paper that Ivan and Carl and Robin Bloom-Cahoot, if you know him, wrote at UNM 20 years ago or something. But I just really like this quote. So what they were looking at was resource requirements for quantum computing. And what they said is that the primary resource is Hilbert space dimension. Now, I think, you can correct me if I'm wrong, I think what you were thinking about was the Hilbert space required to run quantum algorithms. But in addition, of course, when there's noise, we need more Hilbert space just to do the error correction, because we spread our information out in clever ways over a really large Hilbert space so we can detect and correct errors. So typically, to define error correcting codes, we need to get this Hilbert space from somewhere. The standard approach is to look at the tensor product space of a whole bunch of physical systems. Let's just assume they're fundamentally two-level systems. You get some big Hilbert space that scales exponentially in the number of these qubits. Bosonic codes work with the idea that there are physical systems that have inherently large Hilbert spaces to start with. So whichever approach you use, you need to go through this little checklist to see if you're doing anything useful. How are you encoding your qubit over all of these, over this large Hilbert space? How are you going to measure it and manipulate it and do all the things you need to do your quantum computation or whatever else you're doing? And of course, in the presence of errors, which is the whole point, how do you detect and correct them, do recoveries, and so on? But at the end of the day, after you've gone through all this trouble, was it worth it? Meaning, did you reduce the level of noise on your qubits compared to doing nothing at all? And the answer is no, you're wasting your time. So how do we do this in a quantum harmonic oscillator? So I showed this picture on the previous slide. I forgot to tell you what it was. These are the wave functions for the energy eigenstates of a quantum harmonic oscillator. We don't have to use these states. I just put them here because they're nice to look at and you're probably familiar with them. And I want you to connect with the slides. So the whole idea, and it's not particularly complicated to begin with, is just to choose two orthogonal states within your large Hilbert space. And those states define a two-dimensional subspace into which you encode your qubit. And the rest of Hilbert space is for error correction, if you do it cleverly. And what this does is it projects errors that happen on your physical system. So, if you're talking about an electromagnetic mode, like an optical mode in free space or a microwave mode in a cavity, loss is usually our biggest source of errors, which acts on the whole mode itself. But what this does is it projects the physical CV errors into qubit level errors. Some errors happen, you do error correction, and this projects the errors onto to errors on the qubit. And if those are not sufficient, if the errors are still too high to do whatever you want to do to run your algorithm, it's just a qubit at that point, and you can concatenate with higher level qubit codes, surface codes or LEPC codes or whatever fancy codes you're thinking about. So we're going to be thinking about this lowest level. And just to give you an example, which is a little bit concocted, but this is our enemy. This is the biggest enemy. This is loss. This is the annihilation operator. It's not really the loss channel. When you apply this is like a heralded single photon loss event. But that's fine. This is just for illustration. So here's the challenge. We would like to encode some state. So that is the state above that we'd like to encode. The quantum information is the two amplitudes. That's what we want to preserve through some error correction process. The simplest possible thing you could think of is to use the two lowest energy eigenstates, the vacuum and the first excited state, the single photon state in optics. And you encode your qubit like that. And then what happens when you hit it with loss? Well, this annihilation operator maps both of these code words to the vacuum. So it destroys all of your encoded quantum information. So you can't do error correction with respect to loss with this state, with this encoding, but it is a nice benchmark which we can use to compare other bosonic error correcting codes to. And so this is the trivial like lowest energy encoding. So what if we did something a little bit more clever, where instead of this, we use as our zero state some particular superposition of Fock states. Then you can see if you hit that with the annihilation operator, you get mapped to a new Hilbert space, but the amplitudes are preserved. That's great. That means the quantum information is still there and we have access to it. The problem is, if there's another photon loss, the information starts to get distorted, and a third and a fourth one would eventually take you back down to the vacuum where everything's lost. So what you need to do is some sort of corrective process. Once you recognize that an error has happened and your information lies here, you want to do a recovery that takes you back into your original code. So that recovery for this particular code requires mapping you from 1 to 2, maybe that's easy, 3 to some superposition, not necessarily trivial operations, but that's not really the point here. The point is that if you can do it, you bring yourself back to the original code, which makes you more resilient to future losses. So this is the smallest binomial code. There's a family of codes that was proposed in 2016 for a single mode, which is defined as particular superpositions over Fock states with binomial coefficients. That's why it's called binomial codes. And it's a single mode. It's basically based on this much older proposal for specific codes for amplitude damping over 2 modes. Oh, and this is the Wigner function, so the phase space description for the maximally mixed state of some particular binomial code. Another class of codes that you may have heard about are cat codes, which involve code words that are particular superpositions of coherent states. These were also proposed a long time ago, in the late 90s. And this again is the code space, or the mixed state for some particular cat code. And at the time when these things were proposed, we didn't have the technological know-how to do anything. These were like extremely exotic things. But 10 years ago, people started getting really good at manipulating the state inside superconducting microwave cavities using transons and so on. So both of these codes were realized in this setting very recently. And just a few weeks ago, the Chinese group, and I think it included some other people compared to this one, demonstrated some sort of beyond break-even experiment. So we start doing actually better by doing this encoding and error correction. But I put up these 2 Wigner functions because I wanted you to see that in both cases, these Wigner functions exhibit some degree of discrete rotation symmetry. So you take each of these and you rotate it by a particular amount, and you get the same state back. So we recognized this too, me and 2 collaborators, Josh Coombs and Arne Grimsmo, a few years ago. And we realized that there is a much larger class of codes that these 2 fall into that exhibit discrete rotation symmetry. So the way this works is you choose some positive integer, which is going to be your order of discrete rotation symmetry. For those of you that are familiar with GKP codes, this is similar to like choosing the distance between the spikes in each of those Dirac combs. From this, you define a rotation operator that rotates you by some rational fraction of 2 pi. And you can define a code which is invariant under these rotations. So in any code of this type is in the +1 eigenspace of this operator. So in some sense, it's like a stabilizer. The weird thing, potentially, which was interesting to us, is that for a given order of discrete rotation symmetry, that forces the state onto a particular set of Fock states. So for order n, any state that only has support on every nth Fock state is in the +1 eigenspace of that operator. So this gives you a very generic set of states. So, oh, by the way, then you just take the even and odd multiples of n. The even ones become the 0 state, and the odd ones become the 1 state. But I didn't tell you which coefficients go in front of which Fock states. That's a degree of freedom that's left open. And that's why you can have things like cat codes and binomial codes with the same order of rotation symmetry. They just have different coefficients in the Fock basis. Maybe I should have shown this first. This is what happens for like an n=4 code, is that the code itself only has support on this set of Fock states. And this is a symmetry that a physical state can exhibit. whereas the translation symmetries, which I'll get to later, of a GKP state cannot be exactly fulfilled by a physical state. That's what Nick was talking about, needing to use approximate states, because translation symmetry is not like an energy conserving. Displacements aren't energy conserving. Anyway, so this is an example. This is just one example of how they can perform under errors. This is the performance under an equal loss and dephasing master equation. So you let it run for some total amount of time, giving you a total error rate along the x-axis, and then you look at the average infidelity. And what you want to do is beat this break-even. The break-even line is the one where you just encode into this trivial encoding, the vacuum in the one photon state with no error correction. Anything that does better than that, anything below that here, you can say is performing better than the simplest thing you could think to do in your mode. And each of these curves is for a different order of rotation symmetry. Okay, so that's a set of codes defined with respect to one type of symmetry, this sort of discrete rotation symmetry. Nick told you about GKP codes, which are defined with respect to different symmetry, translation symmetry. And in fact, well, I'll just give you you've seen a slide similar to, I thought I deleted that. Anyway, the code states for this code are particular superpositions of position eigenstates. So this is the position wave function, and this is the logical zero state. And the momentum wave function, or sorry, the position wave function for the logical one state is the same thing, just shifted over. And this shows you right away that a position shift by root pi gives you a logical x. And if you look at the same thing in the momentum basis, the Fourier transform of a Dirac comb, which is this function, is another Dirac comb, just with potentially different spacing. So if I were to show you this picture in the other basis and the plus and minus states, you'd see that a momentum shift by root pi gives you the other Pauli. But again, these states are not physical. Anything we can do in the laboratory or in a physical setting is going to require some approximation to those states. One way to do that is to take each spike up there and replace it with a little Gaussian tooth, and then have a big envelope that damps spikes far from the origin. This ruins one thing which you might really want in an error correcting code, which is orthogonality of the code words. But it ruins it in a minimal way that doesn't turn out to be super consequential. So yeah, I think Nick kind of went through this a little bit, but who cares? This thing seems so exotic. Why is there so much fuss about it recently? Well, one, and Andrew might argue a little bit with this, but in a numerical study, some guys found that GKP codes were the ideal code when you have pure loss. So what they did is they just started with some random code and had some iterative scheme, said all we have is the pure loss channel. And their simulations just popped out a GKP code, a super crazy, in phase space with a bunch of little spikes like on a lattice. The problem is dephasing. GKP codes do not perform quite so well with respect to dephasing noise. So unknown rotations. That has been studied less in the literature. But I think one of the main reasons that we like GKP is because of the easy Clifford gates. So Nick told you in the previous slide that you can do all the Clifford gates for GKP using Gaussian operations. And in optics, that's important because Gaussian operations are the only thing we know how to do, basically. You can do the passive ones with beam splitters and phase shifters. And with squeezing, you can do active Gaussian operations. So that allows you to do all the Clifford stuff, and all the Clifford stuff is all you need to do error correction. So as Nick also told you, we realized that if you perform error correction on states outside of the code space, trivial states, the most trivial state, the vacuum, you can use that to produce distillable magic states and get the fault-tolerant universality. You still have to deal with that. Well, given the resources that allow you to do the Clifford part, it's true. It depends where you start counting. And we thought, good point. You still have to make the states. That's the hardest part. And also, as Nick said, GKP code is kind of plug and play with continuous variable cluster state quantum computing, which is a measurement-based approach to quantum computing that I'll tell you a little bit more about, although you heard some from Nick as well. So what's the history of GKP? Well, 20 years ago, it was proposed and it was a crazy idea. And I don't know how much attention it got at the time. I don't know, anyone who was around probably thought it was a pretty idiosyncratic idea, right? Yeah. Yeah. But, it's back. Sorry? Yeah. But GKP is back, right? And one of the reasons of the technology, just like the other codes, it was realized in the motional mode of a trapped ion for the first time in 2019, and soon after in a superconducting cavity. But in optics, we haven't made GKP states. And the reason is that we don't, in optics, have access to strong nonlinearities, whereas that was the whole key to making the GKP states in both of these architectures. So we don't have a strong unitary nonlinearity, but what we do have is a strong measurement-based, like non-deterministic nonlinearity, which is the photon resolving detector. And there's a handful of schemes out there, none of which have been implemented yet, but the idea is to produce a large entangled Gaussian state and do photon number resolving detection on some of the modes. And if you get the right outcomes, what pops out of the final unmeasured mode is some approximate GKP state. So hopefully we'll have one soon. What do I have left? A minute or two? Oh, sweet. Okay. Okay, you've seen this slide basically in Nick's talk previously, but why does this fit so well into the idea of these CV cluster states? So I'm going to do this kind of visually. Each of these balls right here is just a zero momentum eigenstate, so like infinitely squeezed momentum eigenstate. And we take these two states, which are Gaussian, couple them together with this particular Gaussian unitary, which is the CV analog to a controlled Z gate. This is, again, just some Gaussian state. And we make a chain of these, a linear chain of these. This is a linear CV cluster state. And what we can do is attach via that same Gaussian entangling gate any state we want. This one doesn't have to be Gaussian, this could be whatever. And we can do a computation just by performing measurements. And the type of measurement is Gaussian too. It's just a homodyne measurement. So we do a homodyne measurement on this state here, on this mode here. It teleports the state to the next mode with a Gaussian operation applied to it that depends on the basis in which we do the homodyne measurement. So it's not outcome dependent, it's basis dependent. That's important because it's deterministic. Then we repeat this process and we can teleport this state down the line and apply to it any Gaussian operation we'd like. That should make a lot of sense with respect to GKP, right? Because Gaussian operations let you do the Cliffords for GKP. So this is great. This is the toolbox we need to play with GKP states. That was just single mode Gaussian operations. If you take a bunch of these linear cluster states and entangle them together into a two-dimensional version, then you have the ability to implement a multi-mode Gaussian unitary. So you can do all the other two-mode gates that you need with your GKP qubits. But as Nick said, we can't even make the cluster states because they require infinitely squeezed momentum eigenstates. What we have are finitely squeezed approximations to those. And what that does to this computation is the finite squeezing noise gets injected into the computation at every single measurement, and it accumulates. So you have to do error correction along the way, even if you started with GKP states to begin with. And the way you do that is you simply replace some of these zero momentum states with GKP states. In fact, this object here is a GKP bell pair. And if you teleport through an encoded bell pair, not just in this setting, but in any setting, it implements error correction. Well, you have to do the recovery, but this projects you back into the code space. And what Blaney and Nick and I realized, along with Raf, who's not here, is that you don't even have to make the bell pair locally. You can separate the pieces, and each of these will do kind of half of error correction. And this allows you to create hybrid cluster states like this, where some of the modes are zero momentum eigenstates and some are GKP states. This is useful because using that scheme to create GKP states that I talked about, it's not deterministic. So you might have some probabilistic source, and every once in a while it's spitting out GKP states. You can populate your cluster state with as many as you have, and if the fraction gets high enough, you can do fault-tolerant things. That's what these guys studied here. That's what the Xanadu architecture is all about. Last slide, basically. So again, yeah, Nick and Tim and some other people started thinking about computing with CV cluster states in 2006. And this is the continuous variable version, not the GKP version. And people started making them just a few years ago in multiple labs. And more recently, implementing these measurement-based Gaussian operations. So that kind of the primitives that you need to do this type of quantum computing. So we were talking yesterday about how John got frustrated with Wikipedia. So I decided he wasn't around to see ChatGPT 3, but I'm sure a lot of you have played with it recently. So I decided I would ask. And it looks like he would be as frustrated with this as he was Wikipedia, potentially more, because then I did it for Gavin. And it turns out, yeah, Gavin is the president of AIP. So someone has not gained significant notoriety. I should have, but I tried a bunch of other people. However, this might make him happy. What? Hartmut? Oh, well, I spelled it wrong in both cases. So you guys should open up ChatGPT right now and check. Anyway, that concludes my talk. Thanks for having me here. So if you have questions, I can take them. And lots of modes. Right. Well, there's a company out there that's dedicated to doing this, and they have more resources than the average academic lab. But there is an academic lab, which is Akira Furusawa's, who are also trying to do this. And they had a paper from a few weeks ago discussing some of the ways using photon detection to produce not only zero states but magic states as well. So I don't know. I don't work in the lab. I think it's a difficult thing to do, but I don't see any reason why it can't be done. There are technological challenges. Yeah. Well, is 1 time in 1,000 too rare for you? I mean, it's we get to decide. Like, if you have a rep rate that's very high, okay. Yeah. So I guess it's just. Well, this isn't that crazy though. On another side of quantum computing, we already have magic state factories, which have this property where you're dedicating a huge part of your machine just to making one particular thing. This is in spirit, the same idea. So the answer is I don't know. I think it's possible.